starting off with the program initialization, record handling functions, and simulation data structures. So the first contributor establishes the structural foundation of the toolkit by defining the program-wide imports, global variables, and permanent data containers required for hydrologic analysis. Core libraries such as datetime, math, CSV, pandas, and numpy are imported to support timestamping, numerical computation, data manipulation, and file operations. This section constructs the Global Simulation State Dictionary, which houses all major hydrologic inputs, including reservoir levels, elevation area tables, spillway parameters, hydrographs, and routing constants. This section also implements the record management system composed of the functions menu add record, menu view record, menu edit record, and menu delete record. These functions maintain a list of saved scenarios and allow users to create, modify, and store simulation datasets. Each function is structured with validation logic and simple list operations to ensure reliability. By establishing foundational code structures and defining the data models used throughout the program, functions in this section ensures that all subsequent hydrologic processes operate using a consistent and organized computational environment.
The second portion of the program focuses on the creation of the toolkit's menu-driven user interface, enabling flexible, nonlinear navigation throughout the modeling process. This contributor builds the complete simulation menu through the functions simulation menu, display simulation state, edit section, and update functions like the edit reservoir inputs, edit LM area, edit spillway inputs, and the edit inflow hydrograph. These functions implement the principles of user-controlled modeling by allowing the modification, viewing, and clearing of any dataset at any point in the simulation. A critical innovation here is the interrupt keyword system, allowing users to type menu inside any input prompt. This is implemented through the conditional checks inside every input function once the keyword is detected. The program instantly redirects to simulation menu function before returning back to the original workflow. This mirrors field engineering practices where adjustments often need to be made mid-analysis. By designing this flexible control structure, it creates a responsive, user-centered interface that ensures the accuracy and revisability of all hydrologic and structural data.
Now, for the hydrologic computation functions and engineering formula implementations. This part develops the core analytical and mathematical engine of the Reservoir toolkit. This section implements the interpolate x, x1, y1, x2, and y2 function, which performs linear interpolation. When we say interpolation, it is a fundamental technique in hydrology used to estimate missing values between two measured elevation area pairs. This function then integrates this into the compute storage LF area table target LF function, which uses a trapezoidal rule to compute storage volume, reflecting the geometric principle of integrating area across elevation layers. Now, to determine the discharge, the spillway discharge CLH function applies the standard rectangular Ware formula. Q is equal to CLH raised to 3 over 2, a widely used hydraulic equation for free overflow spillways. The routing component is built through the function linear reservoir routing, inflow dtk, and S0, which solves the mass balance continuity equation as nu is equal to S plus I minus 0 delta t at each time step, representing the decreasing behavior of a linear reservoir system. Visualization is then supported by the function assay plot values, which generates text-based hydrographs for field-ready hydraulic interpretation. Additional safety logic is implemented through community alert indicator and warning message, which interprets spillway head and flow trends to categorize flood risk levels. These functions provide all mathematical, hydrologic, and engineering computation required for accurate simulation.
So the next part of our program is the structured input functions for hydrologic and structural parameters. So this part focuses on creating input-driven modules that gather all required simulation data in an organized and validated manner. There are functions such as get reservoir levels, get elevation area table, get spillway inputs, get inflow hydrograph, and get routing parameters that guides the user in entering elevation values, surface areas, spillway coefficients, inflow sequences, and routing constants, where each function incorporates error checking loops using check-stop blocks to ensure that hydrologic inputs remain within valid numerical ranges. Moreover, we integrated menu access logic in this function so that the keyword menu can interrupt input collection and open the simulation menu for data review or correction when the user wishes to or prompts to. So the structure of these input functions reflects engineering standards for hydrologic modeling, where elevation area curves, hydrographs, and spillway properties must be collected consistently before performing flood routing. By establishing clean, validated, and flexible data acquisition pathways, we can ensure that all computations performed later in the simulation are based on complete and accurate datasets.
So in this section, we develop a program logic that unifies all components into a fully functional simulation engine. The central function, which was mentioned earlier, the run simulation function, operates the entire modeling sequence. It calls all the input functions as it passes and collected data into the computational functions. It also processes storages and flows, and it also generates BSCE hydrographs. It computes alert levels and prints the complete summary of the results. This also generates the record system into the computational workflow, enabling users to save inputs, revisit their previous runs, or clear stored scenarios. At the program's highest level, or the main function, the main loop provides global navigation options, allowing the users to start new simulations, manage records, assess menus, or exit the toolkit. Input handling inside the main function ensures that correct selections are properly validated and that control returns clearly to the menu after each action. Through this layer, we ensure that all mathematical, structural, data handling, and the menu components operate as cohesive hydrologic modeling system, completing the program's operational lifecycle. And in using the program, I'll be presenting a trial using a data we collected from research concerning the Angat Dam, and we will test and see how accurate our program is. And just consider that some information are not as classified and may or may not be true to real-time data.
The comparison between the field toolkit and the HEC-HMS Angat Dam study shows a strong conceptual alignment in terms of the fundamental processes of a reservoir operation. Both systems simulate the transformation of inflows into storage and subsequent outflows, capturing the essential dynamics for flood routing through a reservoir. However, the field toolkit simplifies many aspects of the professional HEC-HMS model. And while HEC-HMS employs distributed modeling with detailed rainfall to runoff transformations, routing, and operational spillway control, the field toolkit is user-driven and it relies on manual inflow inputs. And despite these simplifications, the toolkit retains the core hydrologic and hydraulic principles, including storage computation through the trapezoidal area method, spillway discharge based on the rectangular weir formula, and linear reservoir routing to simulate outflow attenuation and delay. Though exact numerical matches are not expected due to the model simplifications, its outputs, hydrograph shapes, peak flows, and the storage volumes align conceptually with historical Angat Dam data. Interactive features like BSCE hydrographs, pandas table, and flood alert indicators enhance usability for education, scenario testing, and community awareness, allowing users to explore how reservoir and spillway changes affect flood risks, even if precision is lower than professional models. Once again, we are Group 3, and this is
The Field Toolkit for Reservoir Flood Routing and Discharge Modeling.
the tool, the model, the mission.